All right, folks, welcome to the first online lecture of Fundamental Physics 1. This is actually kind of a redo of the lecture I gave you on the Wednesday before spring break, but I thought it would be useful to kind of review some of the stuff we did then. So we talked about when does a body start to fall? Obviously, it's when it reaches the edge. As soon as it goes off the edge, it starts to fall because the force, there's a net force, and the net force, of course, is the force of gravity. So once the edge is reached, the force of gravity takes over and things begin to fall. Okay. So in class, we kind of showed that using our law of force and motion, we can figure out how does the velocity change. Okay. So how does V change? Okay, well, let's look at delta V is F net divided by M delta T. Okay. In this case, the net force is the only force acting, and that's the force of gravity. So let me just change colors here for a moment to green. And we know that F net is the force of gravity, which is M times G. So if we put mg in for F net, that will mean that delta V is equal to mg over m times delta t. Well, you know what? The m's just cancel out, and so that just means that your change in velocity is going to be equal to g times delta t. Now, in a previous chapter, what we said was that g was the field strength of the gravity. So g was 9.8 or approximately 10 newtons per kilogram. But it turns out g is also a, so it tells you how much force per unit mass gravity has. But that's also telling you the acceleration, because if we play with the units, we find that 10 newtons per kilogram is the same as 10 kilograms meters per second squared divided by kilograms, and the kilograms go out, and we find that that's the same thing as 10 meters per second squared, which is the same as 10 meters per second. Okay, and so basically, the change in velocity, delta V, is going to be 10 meters per second every second that it falls downward. It's always downward, down. Okay, so what happens when objects fall to the ground? The object undergoes constant acceleration downward due to gravity. Okay, the acceleration of gravity at the Earth's surface is, we're going to be using A and G sort of interchangeably here, because G is the only acceleration we're using. So most of the things I'm going to say about acceleration is true no matter when you have what kind of acceleration you have, as long as it's a constant continuous acceleration. But in this case, A and G are pretty much synonymous. So where you see A, I mean also G. Now the precise number is 9.8 meters per second. Okay, but for simplicity, we're also always going to, or not always, but often use the approximation that G is equal to 10 meters per second. Okay, so for an object dropped from rest, the downward velocity at a certain time, so if you drop a ball, its initial velocity is 0. You just drop it. You don't throw it up. You don't throw it down. The velocity that it has a second or 2 or 3 seconds later is just the change in velocity due to gravity. Okay, so it's going to be delta V hang on a second. Let me, I want to get my arrow back. Okay. It's going to be g delta t, or 10 meters per second times delta t. So a falling object will gain 10 meters per second of speed downward every second that it falls. Okay. Now, what if you launch an object upward? Well, if you launch an object upward, gravity immediately, when it leaves your hand, will start slowing it down. Okay, if it's going up, the acceleration is still down, which means we could think of it as a deceleration, but it just means that the upward speed is decreasing by 10 meters per second per second. Okay, so an object launched upward will decrease its upward speed by 10 meters per second every single second. Okay, we could call this a deceleration, but because we don't want to use different words for the same thing, we just call it a downward acceleration. If it's opposite the upward motion, just as we learned in the first couple of chapters, it means it's slowing down. Whenever you are changing your velocity in the opposite direction from the velocity you're going, it's slowing down. And that means there's a net force in the opposite direction. So if you throw an object upward, the net force is in the opposite direction. It slows it down. Okay? Now, it turns out that the distances traveled by falling bodies was discovered by the great scientist Galileo about 4 centuries ago. And I had a really cool video to show. I will try to link to that video at a different time, but I could not play it here on my my PowerPoint, unfortunately. I don't have the appropriate codec, apparently. So I'll try to show that to you. But the basic idea he found was that whatever distance an object fell during the first unit of time, let's say that unit is 1 second, whatever that distance was, the distance it fell during the second unit of time was 3 times greater. Okay, and the distance it fell during the third unit of time was 5 times greater than the first time. So if we call this unit I don't know, let's call it a Galileo. If during the first second it falls 1 Galileo, then during the second it will fall 3 Galileos, and during the third second it will fall 5 Galileos. Okay, now in fact, we know that a Galileo is approximately 5 meters. Okay, so the total distance fallen then would be 1 Galileo during the first second. If we want the total distance fallen during 2 seconds, it would be 1 plus 3 or 4 Galileos. And then during the 3 seconds, it would be 1 plus 3 plus 5 or 9 Galileos. So the interesting thing here is that the extra distance it falls each successive second seems to follow the odd integers. But what's even more important is it seems that the total distance that an object falls is proportional to the time squared. These numbers are perfect squares. 1, 4, 9. And if you kept going, you would find the next one would be 16, and the next one that would be after that would be 25. Okay? So the total distance fallen is 1 unit after 1 second, 4 units after 2 seconds, or 9 units after the third second. Okay. I had another really cool demonstration video, but that'll have to wait for another time. Okay, so the total distance fallen is proportional to the time of the fall squared. Okay, you could find, in fact, experimentally, that the distance fallen is equal to 1/2 times the acceleration times the time squared, or it's 1/2 at times t. Now, for falling objects, as I said again, what we're going to use is g for a. So when I say a for falling bodies, it really means g, 10 meters per second per second. Okay, so a simple way to understand the distance fallen is 1/2 att. Okay, let me get my arrow back, or my drawing thing back. So after 1 unit of time, after 1 second, the object starts out with a velocity of 0 meters per second, right? 0 meters per second. It's not so easy to draw with. Okay, after 1 second, it will be going approximately 10 meters per second. After 2 seconds, at this point, it will be traveling at 20 meters per second. and after 3 seconds, it will be traveling approximately 30 meters per second. Okay. So that means that the distance fallen during the first second, the distance is going to be the average velocity times the time. Okay, average velocity times the time. Well, as long as it starts from rest, the average is going to be the final plus the initial, and the initial is going to be 0, divided by 2. Okay, so it's going to be v final plus v initial divided by 2 times t. Well, 10 meters per second is just a times t. It's just the acceleration of gravity times t. So basically this here is a times t plus 0 divided by 2. And a times t divided by 2 is 1/2 at, and then you multiply it by t, and what have you got? You got 1/2 att. So that's where we got the 1/2 at squared from. Okay, it's also 1/2 at squared. I prefer to use 1/2 att just because from experience I have found that physics students have the hardest time remembering to square the t. I even do it occasionally sometimes, and I've been at this for many, many years. Okay. So this distance then is going to be the average between 10 and 0 is 5. 5 times 1 second, the distance is 5 meters per second, which is 1/2 at, times 1 second. And that's going to be 5 meters. Okay. For the first 2 seconds, what's this distance going to be? Well, it's going to be 4 times that. It's going to be 5. That's going to be 20 meters. But let's just do the math. The distance is going to be 20 meters per second divided by 2 times 2 seconds. Okay, so I get rid of the 2 seconds, and we find that it's equal to 20 meters. Okay, all right, I'm running a little short on room here, but for 3 seconds, okay, for 3 seconds, we find that the distance is going to be 1/2 of 30 meters per second plus 0, right, times 3 seconds. So 1/2 of 30 is 15. 15 meters per second is the average velocity during the first 3 seconds. So it's got an average velocity of 15 meters per second during the first 3 seconds. You multiply that by 3 seconds and you get 45 meters. Okay? So be very careful when you use an equation like this, 1/2 att. If you just memorize it and plug in numbers, you're really not understanding what it is, but it's very easy to understand it because the 1/2 at is the average velocity. So whenever you drop something from rest, you don't even need to use that equation. You could just kind of do it in your head. You can say, I start at 0, I end up at either 10 or 20 or 30 or 40 or whatever, and you average that out. You take the, split the difference, find out what half of it is, and then you multiply by the number of seconds, and that's the distance fallen. Okay? So do this example. How fast will a falling baseball be traveling after 4 seconds, after it's dropped from a tall building? I'd like you to pause the recording right now and try this on your own. Okay? Then start it again when you get an answer. Okay, hopefully you've got the answer. Let's go through the answer. And please try these on your own before you look at the solution that I give you. Okay? The answer, delta V, is the change in velocity is acceleration times time. In this case, the acceleration is the acceleration of gravity. Okay, so that's 10 meters per second per second. The time is 4 seconds. And that means that it gains 10 meters per second each second. So it goes to 10, 20, 30, 40. So the answer is going to be 40 meters per second. Okay, all right. I've run out of my 15 minutes of time for this lecture, so I'm going to continue this in part 2 of the falling bodies lecture.